I'm going to open up a file here. Just got to remember when I made it. LT Spice. I think I made it last winter. Nope. Last spring. All right, so here's a big schematic down. You guys don't need to really copy any of this down. I just want to talk about what's going on here. Okay. So for this particular schematic, my power supply stuff is exactly the same as what we had done in class on Monday. It's totally Wednesday. I simply have 10 volts for VCC plus, negative 10 volts for VCC minus. I have a reference voltage of 3 volts. And then I have a sinusoidal input voltage that has an amplitude of positive 10 volts and a frequency of 1 hertz. So it's 1 cycle per second. And then this one way out here on the right, after all these zeros, is I'm just restricting my sinusoidal source to generate exactly 1 cycle of the sinusoid. The different thing here is on top of it, I have a behavioral voltage source that is going to be generating white noise. So it's going to cause my total input signal to be that pure sinusoid with a little bit of noise on top of it. And we'll look at it in a minute. And then here in the middle of the circuit, I have a simple non-inverting comparator. So if I run a simulation here and I look at my input signal with that little bit of noise on top, we can see that it's exactly how I described it. A 10 volt sinusoid in amplitude with a little bit of noise on top. Oscillations, both positive and negative. And if we look at the output signal of our comparator, we have some wonkiness, okay? And the wonkiness comes from the fact that our open loop voltage gain is so high that if this small amount of noise pushes our signal below our reference level or above our reference level, we're getting oscillations in our output signal as we have oscillations around our input signal, which isn't necessarily a good thing, right? We're expecting a simple binary output of either high or low, and we're getting it, but we're getting wild swings when we have a noisy signal. Over here on the very right-hand side, I have what's called a Schmidt trigger circuit. And the Schmidt trigger circuit uses positive feedback to generate some latching. So if I look at my output signal for my Schmidt trigger, this V out 2, I see that I have a smooth transition from low to high, and then a smooth transition from high to low, but my reference values are a little different, right? So we can estimate here, I'm transitioning from low to high at somewhere about 7 volts. And I am transitioning from high to low at somewhere about 1 volt. So what we are going to do is we are going to analyze this circuit using our practical op-amp model and see if we can develop some sort of mathematical relationships to where we can predict where this upper trigger limit and lower trigger limit is, so that we can use that for the design of a Schmidt trigger circuit. Okay. So let's draw things out here. So this is positive feedback circuits. And the first one that we are going to talk about is the non-inverting Schmidt trigger. which looks like this. So we have our op amp. Here's our positive supply voltage, VCC plus, our negative supply voltage, VCC minus. We have positive feedback, so we have a resistor in a feedback path between our non-inverting input terminal and our output terminal, and I'm going to call this resistor R2. Here is our output node. So V out. We apply our reference voltage to the non-inverting, the inverting input pin. And then we had some resistance, which I'm going to call R1 here between our input signal and our inverting input pin. Okay. So this is what we have in our schematic diagram. Now we are going to draw the equivalent circuit for this using the practical op-amp model. Okay. So I'm going to start with just the general op-amp model. I have my input resistance here, Rn. This terminal, V plus, is going to be my non-inverting input terminal. This terminal down here, V minus, is my inverting input terminal. And as always, my differential voltage VD is simply the difference of these two pins, the voltage difference between these two pins. Drawing the output side of things, I have my dependent voltage source, AVOL times VD. Here is my output resistance, R out. And here is my reference. So my output voltage is measured as the open circuit voltage here. So let's do some other connections here, okay? So between the inverting input terminal and ground, we have our reference voltage. Between the non-inverting input terminal and ground, we have a resistance R1 in series with our input voltage source. Like so. And now we have, the only thing left is our feedback path. So from our non-inverting input terminal to our output terminal, we have that resistance R2. I'm just going to scooch this guy over a little bit. We are going to make some assumptions here, okay? And these are effectively the assumptions that we talked about at last class. So we are going to assume that the values of R1 and R2 are significantly smaller than our input resistance, and they are significantly larger than our output resistance for the exact reasons that we talked about in the last class. And that is going to help our circuit analysis a little bit as well, okay? So R1 and R2 are much, much smaller than Rn, and R1 and R2 are much, much greater than RL. Those are the assumptions that we're doing here. So we are going to apply Kirchhoff's current law at our non-inverting input terminal. But we are going to use these assumptions here to make things a little bit easier. Okay, so let me talk about what this assumption, this one up top, specifically implies, right? So we have our input voltage connected to some resistor Rn. And then we have this node here where our resistor R2 is connected to resistor R1. This is forming our feedback network. But then we also have this branching path right here through our input resistor. Okay. So if R1 and R2 are much smaller than Rn, what did we observe in class on Monday? Current flowing through those resistors was much smaller, or excuse me, the current flowing through R1 and R2 was much greater than the current flowing through our input resistance. So we are going to say that there's effectively no current flowing through the input resistance. Okay. So this is part of our assumptions here. This current, let's call it IN, is effectively zero. If there's no current flowing through this resistor, there's not really a voltage drop over it either. So our reference voltage is effectively here. Now we're going to write a KCL equation at this node. Okay. So we're going to add this current plus this current together and set them equal to zero. And then we're going to do a little bit of algebra. You guys have a question? Two squiggly equal signs, approximately. No, not a percent sign, just approximately VREF. So if we write our KCL equation, KCL at the non-inverting input, what we will have is VREF minus VN over R1 plus VREF minus V out over R2 is equal to zero. And so all I'm going to do now is just a little bit of algebra here. Okay. So I'm going to move both the input and the output voltage to the right-hand side of the equal sign. So that's going to give me VN, just give me V reference times a factor of 1 over R1 plus 1 over R2 will be equal to VN over R1 plus V out over R2. What's this thing right here? The reciprocal of parallel resistances, right? Because if it were 1 over R1 plus 1 over R2, it would be parallel resistances. So effectively, this is the same as R1 plus R2 divided by R1 times R2. Okay. So I'm going to multiply this side by R1 times R2 over R1 plus R2. And we'll find that VREF will be equal to R2 over R1 plus R2 times VN plus R1 over R1 plus R2 times V out. And this is our characteristic equation, effectively, for our non-inverting Schmidt-Trigger. We're going to play around with this, but this equation right here tells us how this thing behaves. Where our reference voltage, some fixed value, is related to our output voltage, which will be either VCC plus or VCC minus from what we've observed of the behavior of this thing. And then this VN is going to tell us effectively where our trigger levels are. Okay. So let's define some things here. Our upper trigger limit, I don't want to use that color. Or UTL is the input voltage that causes the output voltage to change from VCC minus to VCC plus, right? So the upper trigger limit is the input voltage where the transition from low to high on our output occurs. And similarly, the lower trigger limit is the opposite. So it's going to be the input voltage, LTL, the output voltage to change from VCC plus to VCC minus. So let's calculate the upper and lower trigger limits of this circuit. Okay, let's make a couple of notes here really quick. VREF is equal to 3 volts. Let's do this down here. VCC plus is equal to positive 10 volts. VCC minus is equal to negative 10 volts. R1, I believe I have as 3 kilo ohms. And R2, I believe I have as 10 kilo ohms. Let's just double check, make sure everything seems legit here, right? So we can see that VCC plus is 10. You can see that VCC minus is 10 below 0 or negative 10. V reference is 3. R1 is 3 kilo ohms. R2 is 10 kilo ohms. Right. And just to remind you guys of what we're expecting, our upper trigger limit is between 6 and 8, so somewhere close to 7. Our lower trigger limit is between 0 and 2, so somewhere close to 1. All right. And I'll show you how to look at that more specifically in LT Spice in a few moments here. All right. So if we're trying to determine the upper trigger limit, we have our reference voltage of 3 volts is equal to R2, 10 kilo ohms, divided by R1 plus R2, times our input voltage, plus R1, 3 kilo ohms, divided by R1 plus R2, 3 kilo ohms plus 10 kilo ohms, times our output voltage, VCC minus, right? So let's talk about this specifically because this is where things can be weird-ish, right? So the upper trigger limit is when we're transitioning from VCC minus to VCC plus. So this is the output voltage that we use to calculate the upper trigger limit. We're seeing it transition from this. So VCC minus in this case is negative 10 volts. And we can do a little bit of algebra, right? So we're going to have 3 volts plus 3 over, actually, minus 3 over 13 times 10 volts. All of this times 13 over 10 will give us Vn. My algebra okay there? So I simply moved this term to the left-hand side of the equal sign, and then I multiply by the reciprocal of this thing to get just Vn. So throw that in your calculator and tell me what you get. Actually, there's an algebraic mistake here. When I move this over here, that should be a plus sign. Yeah. Three plus 30 over 13. All of that times 13 over 10. We are trying to figure out what voltage causes our output to change from VCC minus to VCC plus. So we put VCC minus in as our output voltage because that's what it is until we transition. And we'll see the same or the opposite thing, I guess, when we look at the lower trigger limit here in a moment. What'd you get? 6.9. 6.9 volts. Seems reasonably close to the 7 that we observed looking at our simulation. Let's determine the lower trigger limit. We're using the exact same equation. Our reference voltage, 3 volts, will be equal to, I'm going to speed things up here, 10 over 13 times Vn plus 3 over 13 times V out, where in this case, our output voltage is positive 10 volts because we're transitioning from VCC plus to VCC minus. So we're going to have 3 volts minus 3 over 13 times 10 volts times 13 over 10 will be equal to VN. What do we get here? 0.9 volts. Pretty close to the one that we observed. Or around one that we observed. So, my mouse on here. Let me find this. All right. So I'm going to show you guys a little bit better of a way to look and determine what the lower trigger limit and upper trigger limit is based on the graph. This is going to be a funny looking graph, so I'm going to need to explain it a little bit. The first thing I'm going to do though is delete the comparator information. So I'm deleting my input signal because we don't need that. And I'm deleting this guy because that's from the comparator. And what I'm going to do right now is I'm going to change my quantity plotted from time to just my input voltage, which in this case will be the voltage at Vn plus N. So I'm still including the noise in here for whatever reason. And we get this funny looking graph, okay? So this is what would commonly be called a hysteresis loop, okay? And the reason why we have a graph like this is because our Schmidt trigger has latching, okay? So effectively what happens is we look at this graph from left to right. As our input voltage is increasing from -10 volts, we don't actually trigger high until we get here, and then we're at high. Right? Our output is effectively latched at high, and it's going to stay high even as we decrease our input voltage until we get below our lower trigger limit, which causes the output to swing to the negative value. And then this just repeats over and over and over again. So it's low until we hit the upper trigger limit, jumps to high, and then it stays high until we hit the lower trigger limit, and then transitions back to low. If we mouse over these vertical lines, we can see right here, hard to see, X is equal to 0.90 volts, exactly what we calculated. Mousing over this one right here. X is equal to 6.91 volts. So pretty much spot on to what we calculated, even though we made some assumptions about the behavior of this device based on the internal resistances and all of that kind of good stuff. Our model matches very, very well. So this is a non-inverting Schmidt trigger. This is another way that we can make analog to digital converters, except that we get a little bit more wiggle room here. In fact, one of your design problems, I asked you to use a Schmidt trigger to make an analog to digital converter, where instead of arbitrarily saying when it's above this level, it's a digital high, and when it's below this level, it's a digital low. I think I have it. So if the output voltage, if the input voltage is 3, it should transition to high, and if the input voltage drops to 2, it should transition to low, and then you have that latching in between, so that it's not a simple binary decision. Yes, ma'am.
So how exactly is that affected?
So because we have that latching, because the output stays high until we get less than the lower trigger limit, or it stays low until we get higher than the upper trigger limit, those noise variations don't cause the output to change state. Right. Yeah, I mean, if you had an upper trigger limit and lower trigger limit that were effectively the same thing, then you would have a comparator, the pure comparator. But this positive feedback allows us to process a signal that has noise on it, but it splits our reference level into 2 discrete things, right? So it stays high until we get beyond this point, and it stays low, or excuse me, it stays low until we get beyond this point, and then it stays high until we get beyond this point on the return path. All right. So now let's look at an inverting Schmidt trigger. Okay. So for an inverting Schmidt trigger, what do you guys think is going to happen?
Maybe.
We're going to replace VREF with VN. That's it. Everything else is exactly the same. We're simply swapping the terminals at which we apply things. So let's put VREF right here. And let's put VN plus N here. And run our simulation. And now our output stays high until we get beyond the upper trigger limit. And it goes low, and then it stays low until we hit that trigger limit and it goes high. So what's wonderful about this is that we're not going to have to really derive anything. Okay. If we look at this circuit, what's the only change we made for an inverting Schmidt trigger? We swapped the position of those two voltages. We did all of our derivation. And so I would argue that if we swap these two voltages in our expression, we have the same result. Why wouldn't we? Right? So let's just draw it out here really quickly. So our circuit is almost exactly the same thing. Here is R2 connecting our inverting input node, excuse me, non-inverting input node to our output node. So we still have positive feedback. We apply our input signal here. Apply our reference, excuse me, that should be R1. And apply our reference signal here. And then our relationship is going to be Vn will be equal to R2 over R1 plus R2 times Vref plus R1 over R1 plus R2 times V out. And the definition of our upper and lower trigger limits remain exactly the same. The upper trigger limit is the input voltage that causes the output to swing from low to high or from VCC minus to VCC plus. The lower trigger limit is the input voltage that causes the output to swing from VCC plus down to VCC minus. But now we don't even have to do algebra, because Vn is the thing that tells us what our trigger limits is. So we literally just throw our numbers in and have V out VCC plus in one case, VCC minus in the other case, and we have our voltages. Just for the sake of argument, let's figure out what these things should be, right? So with V out set to be VCC minus, this is going to be, let's see, R2, so 10 over 13 times 3 volts plus 3 over 13 times -10. Our upper trigger limit is 0. And I've changed that positive 10, or excuse me, negative 10 to positive 10. 60 over 13. 4.6-ish volts. And if we look, well, I'll be damned, that's pretty much exactly what we have. So the lower trigger limit is where it transitions from high to low. So this is the lower trigger limit here. So it's staying high until we exceed the lower trigger limit, and then it goes low. And then it stays low until we get less than the upper trigger limit, and then it goes high. Yes, Gabriel.
Do we need a white noise to create it?
No, not at all. The noise is completely and utterly irrelevant. I'm just continuing to add the noise in because I'm wanting to show you guys that it doesn't matter whether or not the noise is there. This thing behaves in this particular way, right? The noise is what's messing up the performance of the comparator. And we are fixing that error in performance by applying positive feedback. All right, so we got 20 minutes, or actually we have 35 minutes left of class. I want to look at one other circuit and then we're going to call it a day here. All right. So this is an odd looking circuit for sure. We'll talk about what's so odd about it in just a moment. The circuit that we are going to talk about now is the other big use of positive feedback. Probably the biggest use of positive feedback is to create an oscillator. Okay. So this circuit is the op amp astable multi-vibrator circuit, or a simple oscillator circuit. Okay. So start with our op amp here. Just for the sake of argument, I am pointing out that I'm putting my inverting input terminal on top, my non-inverting input terminal on bottom here. It's not going to change anything. I just want to point that out. Yes, ma'am.
It doesn't really matter which side you're using.
So for a physical op amp, there is a very specific pin that you're supposed to apply VCC plus to and VCC minus to. For my schematic diagrams here, I'm playing fast and loose just for the sake of convenience of drawing it at VCC plus on top, VCC minus on bottom. Yeah, so, but for a real practical op amp, you look at the data sheet and it'll say which one is for the positive supply voltage and which one is for the negative supply voltage. So this is a positive feedback circuit. So we're going to have a feedback resistor between the output terminal and the non-inverting input terminal. So let's call this guy R1. Here's our output terminal V out. I'm going to place a resistor here, R2. Like so. This node down here is going to be my ground. And now I'm going to have some interesting things here. All right. So between my inverting input terminal and ground, I'm going to have some capacitance C. And between my inverting input terminal and my output terminal, I'm going to have some resistance R. So let's talk about what's weird about this thing. Anybody have any thoughts? There's a capacitor there. Sure, that is arguably weird. We haven't dealt with a capacitor in this class before, but we've dealt with capacitors in general. We pretty much know how they work, so that's not really the thing that I'm looking for here. Feedback on both sides, definitely weird. Because we have positive feedback, even though there is negative feedback, we're still going to see that our output transitions from VCC plus to VCC minus. Those are the only two valid states for the output voltage. Anything else that's weird about this guy? There we go. VN doesn't exist in this circuit. Okay, there is no input voltage for this circuit. It simply generates an oscillation if you supply power to it. That's literally its job. Okay, there isn't a specific reference voltage, but there is going to be a reference voltage that is in play here. We're going to call our reference voltage the voltage at this node between R1 and R2. And we are going to look at what happens with our capacitor voltage in comparison to this reference voltage to figure out how this thing works. Okay. So speaking of how this thing works, how it works. Step one, we are going to assume our capacitor voltage is 0 volts. So our capacitor is just fully discharged. And we are going to assume that our output voltage is high, or VCC plus, as our initial conditions. Okay. So if the voltage drop across our capacitor is 0 and our output voltage is high as our initial conditions, we are starting out in a case where there is going to be some current flowing from this node through our resistor around this path. So effectively, our current is going to put charge on our capacitor and it's going to slowly charge up, right? So since we know roughly how capacitors work, we have some idea from our previous experience and all of that kind of good stuff. I'm going to make a plot here. And in purple will be my capacitor voltage, VC. So we are going to see that as time passes, our capacitor voltage increases. And let me write a kind of legend here. VC, and I'm going to make another graph here to be black so that we don't have too many things on the same plot. Here's VCC plus, here's VCC minus, and our green curve is going to be V out. Okay. So what's another consequence of this voltage being positive power supply? Well, our reference voltage is going to be a positive number because we have a simple voltage divider circuit here, effectively. Assuming once again that R1 and R2 are smaller than the input resistance, our reference voltage is just going to be R2 over R1 plus R2 times VCC plus, right? Using voltage division. So Let's do this one in red. Here's our reference voltage. And it's at some value, right? As our capacitor voltage progresses to meet our reference voltage for this case, our output is going to swing to the opposite rail. Our current is going to change direction, and so our capacitor is going to discharge. When our output swings to the opposite rail, our reference voltage swings to the opposite rail. And then this cycle just occurs over and over and over again. So our capacitor charging and discharging causes our reference voltage to swing from a positive value to a negative value, which in turn causes our output voltage to swing from a positive value to a negative value. And because we have a positive feedback system, the output will always be either VCC plus or VCC minus, because those are the only two stable operating points of the system. Yes, ma'am.
What?
So when V out swings negative, this voltage is at a higher polarity than this voltage. So the current starts flowing in the opposite direction. Right? Our reference voltage is now also a negative voltage. So effectively, our differential voltage here changed signs. As soon as this capacitor starts to discharge, our differential voltage changes signs, which means our output voltage also changes signs. Because this thing is just amplifying the difference between Vref and Vc effectively.
So what happens to the passion?
So it's kind of a chicken and egg type thing here, right? The whole system kind of works all together. So let's look at what's happening, right? So when VCC plus is, or excuse me, when V out is equal to VCC plus, this voltage is positive, right? There is a positive, or excuse me, there is a current flowing through this resistor that is causing this capacitor to charge, okay? This voltage is fixed at some positive number. This number is increasing from 0 to getting larger and larger and larger. As soon as the capacitor charges enough to have a voltage that is even slightly higher than this positive V reference, our output changes state. Because the differential voltage went from having a positive sign, right? Because it would be the voltage here minus the voltage here is a positive quantity, to the voltage here minus the voltage here is a negative quantity. And so our output voltage changes to low, our reference voltage changes to low, and now the capacitor is discharging because this point is higher in potential than this point.
So the capacitor keeps charging.
Keeps charging and discharging. It's chasing the reference voltage always. So let's simulate it. Okay. This one is a wonky circuit. I have no doubts that you guys are like, he's pulling this out of his ass. So let's at least partially prove that I'm not. I'm gonna, let's see, let's just make a whole new thing here. Let's move that. So let's start with my op amp. So I'm going to use universal op amp 2. I'm going to leave that alone. VCC plus goes here.
VCC minus goes down here. Gonna make this smaller so I can put other things in. Nope, not that one yet. So there's my resistance R1. Here's my resistance R2. Throw a capacitor in here. Throw a resistor up here. Put my ground node down here. And I need to set up my power supplies. All right, so what do we want to use for our supply voltages? Just hit me with something. 10 and 10, sounds groovy. All right. And let's throw some values at this thing, right? So the values that we use are actually going to set the frequency of oscillation, and I'll give you guys the mathematical relationship here in a moment. Okay. So hit me with resistor values. 2000, all right, so that's 1. What did you say, Gabriel? Okay, well, we're never going to use not kilo ohms. 50 kilo ohms. All right, let's make this one a 50 kilo ohm resistor. Something else. 5K up here. All right, what size capacitor do we want? 200 micro. Stop being a jackass, Gabriel. So I have no idea what frequency this is, so we're going to start with running this for 1 second. Okay. Now, I firmly believe that this is actually going to give us nothing here, and I'll talk about why that is, right? So if we look at our output voltage, which is this pin right here, yeah, we get absolutely nothing. Okay. The reason why we're getting absolutely nothing is because we're using ideal components. So how I'm going to trick this thing is I'm going to give my capacitor a little bit of stored energy by saying that there's a small voltage drop to start things on, right? So we're going to say that the voltage at this node, I'll label it as VC. We're going to put an initial condition on this. .1 volts. That probably is more than it needs to be, but that'll be okay. All right, so we need to run this thing for longer because it is changing. So this is what happens when I let you guys pick stuff and I have no idea what the frequency is going to be. Let's run this for 60 seconds. All right. So we have oscillations. The whole purpose of this thing is to just generate oscillations. There is no input signal whatsoever. In a real system, we wouldn't have to say, oh, there's a little bit of voltage on the capacitor, because thermal noise would eventually drive this thing into oscillations. The random fluctuation of electrons in the capacitor would eventually be enough to start the oscillations. And once they start, they don't stop until we turn the power off. Okay. So, math. Okay. The period here capital T of this, and we just talked about how it works instead of describing it, and that'll be okay. That's what the videos are for, is twice RC times the natural log of 1 plus beta over 1 minus beta, where beta is equal to R2 over R1 plus R2. So effectively, should make a lot of sense. Generally speaking, the time it takes for this thing to go through one cycle is largely based off of the time constant R times C. And then these resistor values effectively give you fine tuning within this relationship. That is what I have for today. So for class on Friday, I'm going to need to wrap things up a little bit early. No, thank you, spam risk. I'm going to be interviewing faculty candidates for the electrical engineering lecturer position that's open. And our first interview is at noon, and our second interview is at 1. Noon corresponds with when we're in this class. So I'm going to try to wrap up by about 11:45 or so. And then obviously I'm going to be tied up from noon to 2. So because my office hours are supposed to be from noon to 2, I'm going to stick around that afternoon. If you guys want to ask any questions or anything like that. So I should be on campus until about 4 p.m. All right. So just to be clear, we are having class on Friday. We're wrapping it up early, and then I'll be around this afternoon if anybody has, or that afternoon if anyone has any questions.